Hello, welcome back to How It All Started LLM Edition. This is Abhik, and in this series, we are tracing the path to our current LLMs by reading the paper that built them. Starting from the first paper, Attention is All You Need. Now, just to recap, paper 1 gave us the architecture, the transformer. Paper 2 gave us the pre-training thesis, train a big transformer to predict the next token on web text, and zero-shot task behavior starts to emerge. Paper 3 gave us the formula, the scaling law recipe that allowed models to scale. And finally, this paper, GPT-3, asks a simple question. What happens when we actually get such a big model? Same architecture, family as GPT-2, but just scaled up on more data for longer. If I had to sum up the paper, what authors try to say is that at this scale, the model starts to learn tasks from just a few examples placed in its context window, with no gradient updates at all, no fine tuning, just text in, text out. That's what is called few shot learning, and we'll go deeper into that. And this is exactly what we are going to walk through today. The setup, the scale ladder, the evaluations, and what the authors learned from that. Now, on the abstract, what the author is saying is we are essentially working with the same type of model as before. Here, it is GPT-3. It is still an autoregressive language model. By autoregressive, we essentially mean that a model that predicts the next token. So this paper is not inventing any new kind of model or a fancy new laws. It is testing one hypothesis. Does scaling up a plain decoder-only language model dramatically improve the task-agnostic few-shot performance, sometimes to the point of competing with the fine-tuned state-of-art? Now let's define the words carefully. Task-agnostic here means that we are not training the model for one particular task. The idea is to train the model in a task-agnostic way, and then it can generalize to multiple different types of tasks. By few-shot learning, we mean essentially is, let's say I want the model to do a task X. Now, instead of training the model with thousands of labeled examples of that task X, I just write a few examples of task X directly into the prompt, then ask it to do one more. So we are not essentially training the model. The model weights never change. It just reads the examples and continues. Now you can understand this is very similar to how humans learn. Think of it like almost showing a coworker 3 filled forms and then handing them a 4th form and saying, your turn. I mean, I didn't really retrain the coworker. We just shown examples in context. That is the few shot setup. And what we measure is a few shot performance. Now for zero shot, it is more 0 examples, only a natural language instruction, and one shot is 1 example. Fine tuning is the old way, where we collect a task specific data set of thousands of examples and actually update the model weights during training. Now this matters because fine tuning needs data for every new task, while few shot needs only a prompt. A big enough model can learn from context alone. You get a single general model you can adapt on the fly with no per task plumbing. Now, when I say fine tuning is old, I essentially say from the context of this paper. Fine tuning, as we will learn, is actually very important in LLMs. But when this paper came out, they were essentially talking about the pre-LLMs era of primarily fine tuning based neural nets. The abstract then gives you the headline. Essentially, what it's trying to say is we don't need gradient updates, we don't need fine tuning. And just by giving few examples, we are able to achieve text interaction, strong on translation, on the fly reasoning, basic arithmetic, so on and so forth. And the paper ends with a broader societal impacts discussion. Now, this one picture, this whole paper is built on this one picture. Now, there are 2 loops in this picture. There is this outer loop and inner loop. Let's take them one at a time. Now, the outer loop is just ordinary pre-training. The model reads a huge amount of web text, and by predicting the next word over and over, it quietly picks up a broad set of skills, grammar, facts, arithmetic patterns, and pretty much what we learned in the other papers. Now, all of that is slow, spread across the whole training run, and driven by gradient descent. So that is the outer loop. Now, the inner loop is this new idea. At inference time, you hand the model a sequence that already contains the few examples of a task. Say a couple of English to French pairs. And within that single forward pass, the model recognizes that task from those examples and just continues the pattern. So there are no gradient steps, no weight changes. And the paper calls this inner loop or in context learning. The model is not being trained on your examples. It uses skills it already has to figure out on the fly which task you want. So put simply, outer loop actually learns the skills and the inner loop picks the right skill out of the prompt and applies it. That's also called meta learning. The model has, in a sense, learned how to learn. And hence, a natural question follows. Then, where does fine tuning fit in this two loop picture? Fine tuning is really just a second outer loop. The same gradient descent, changing the same weights, only run again after pre-training on a narrow task-specific dataset. The inner loop is alternative to it, adapting to the task purely from the prompt with the weights frozen. So the two are two different ways to specialize the model. One rewrites the weights, the other only conditions the prompt. GPT-3's whole bet is to skip the fine-tuning loop and let the inner loop do the work. Now, this is also the direction where a lot of the frontier labs have gone, where they do not make the weights public, so you cannot fine-tune them. And the bet is the inner loop is so good that you can use the prompt-based in-context learning to get your work done. We'll talk about it more later. Now, why does the paper spend so much energy on this? Because the standard way of doing things at that time was opposite. The field had been on a clear path when this paper came out. What vectors, then recurrent neural networks, and then the transformer language models came out. Now, each one is essentially stripping away more of the task-specific machinery. But one thing stayed constant at the very end of that pipeline. To actually do a task, you fine-tune. You collect a task-specific data set, often thousands to hundreds of thousands of labeled examples, and you update the model's weights on it. And paper says at that time that this is limiting. You cannot collect a big labeled data set for every task you might care about. So essentially what the paper is saying, it is incredibly hard to collect data set for every different task in the world. And models fine-tuned on narrow data can latch onto spurious patterns and generalize poorly. Now, what the paper argues is this is not how people work. A person, a human, picks up a new task from a couple of examples or a few lines of instruction, not from thousands of labeled cases. So the paper argues that in-context learning is the solution. Now, the question is, if in-context learning is a silver bullet, then up till this point, why didn't we do it? Well, the reason is, when the paper came out till that point, in-context learning had underperformed fine-tuning badly. This is the approach GPT-2 introduced, and its numbers were far behind. For example, GPT-2 managed only 4% on natural questions, and its question and answer performance was also many points behind the best fine-tuned systems of the day. As a practical way to solve tasks, meta-learning simply was not there yet. And just to define again, we use the term in-context learning to describe the inner loop of the process, which occurs within the forward pass upon each sequence. Now, granted that at that time, GPT-2 didn't perform as well as fine-tuned systems, the authors knew that of the obvious objection going in. Historically, this in-context approach loses to fine-tuning and by a lot. Now, here's their bet. They argue that the gap is not fundamental. It is mostly a size problem. In-context learning have never really been tried at scale. And paper 3 scaling laws gave them a reason to believe that scale keeps paying off, like we saw. Loss falls as a smooth power law as we grow the model. If you remember the graphs that we saw. So, bigger models should keep getting better. So the hypothesis stated plainly is we scale up the model and the data far enough, and in-context learning should improve dramatically enough to start closing the gap with fine-tuning without ever touching the weights. And this figure should tell us why they think so. The x-axis is how many examples you put in the prompt. The y-axis is accuracy. And each bundle of curves is essentially a different model size. The biggest models climb the fastest. They squeeze the most out of each extra sample. The rest of the paper pushes scale 2 more orders of magnitude, all the way to 175 billion parameters, to put that bet to the test. So you can see how the accuracy has gone up as the models have grown larger and larger. Now let's make the GPT-2 versus GPT-3 shift a bit more concrete, because this is the whole argument in one comparison. The numbers in GPT-2 were weak on a bunch of different heads. Now, if we take the exact same transformer family, same next token objective, and scale it up about 100 times, then we see some interesting results. Broadly, on NLP tasks, GPT-3 now gets very promising results in the zero-shot and one-shot settings. And in the few-shot setting, it is sometimes competitive with fully fine-tuned state-of-the-art. It also picks up new tricks, unscrambling words, three-digit arithmetic, using a made-up word in a sentence. The point that the authors are trying to hammer home is that nothing conceptually new was added. The architecture is GPT-2's. The objective is also GPT-2's. The autoregressive behavior is same. The only thing that changed is scale. So whatever got better, we can attribute almost entirely to the model being bigger. Now, this figure is the cleanest evidence for the claim. This is aggregate accuracy across all 42 benchmarks, plotted against model size. 3 curves, 0 shot, 1 shot, and a few shot. Now, if you see the left side is small, the GPT-2 scale models, and the right side is GPT-3 at 175 billion. Now, two things happen as we move right. 0 shot accuracy climbs steadily with size, but few shot accuracy climbs faster. So the gap between few shot curve and the 0 shot curves keeps widening as the model grows. That widening gap is the part to notice. It means the bigger the model, the more extra mileage it gets out of the examples in its prompt. In other words, in-context learning is a skill that gets stronger with scale. The last thing the introduction tells us is to train a huge model on a huge slice of the internet. How it did not simply memorize the test sets. We discussed this in GPT-2 as well. The paper, of course, calls this data contamination, and the authors took this very seriously to build systematic tools to measure the overlap, and we'll go deep into it. But the headline, which they call out here, is they feel the impact of the data is minimal approach. This defines the evaluation settings based on how much task-specific data it relies on. On one end of the spectrum sits fine-tuning, which is the approach GPT-3 is deliberately avoiding. So let's be clear about it first. Fine-tuning. Generally, fine-tuning works like this. You start from a pre-trained model, take a task-specific label dataset, say thousands of sentiment tag reviews, and keep training the model on it, updating its weight with gradient descent until it is good at that one task. Now, it has been the dominant approach for years, and it sets the state of the art on many, many benchmarks. GPT-3's whole page is to match that without doing it. No weight updates at all. But paper first, of course, talks about why fine-tuning is limiting. And the main disadvantage the authors call out is the need for new large data set for every task. And of course, this model would not generalize as well. And the potential to exploit spurious features of the training data, potentially resulting in an unfair comparison with human performance. Now, of course, there are a few ideas packed in here, so I'm going to unpack a bit. First, generalization out of distribution. Distribution just means the kind of data the model was trained on. In distribution is more of the same kind. Out of distribution is data that looks different. A model fine-tuned on movie reviews might ace more movie reviews, but fall apart on tweets or legal text. It learned the narrow slice, but not the general skill. So, very good in distribution, but poor out of distribution. Second, exploiting spurious features. A spurious feature is a shortcut that happens to correlate with the answer in the training data, but it's kind of not the real reason. It's almost like cheating. A classic example is an image model that detects cows by spotting green grass, because every cow photo it trained on had a field behind it, so it fails on a cow at the beach. In language, a fine-tuned model might learn if the review contains the word brilliant, predict positive. Instead of actually understanding the sentiment, it learned the task. It latched onto a coincidence in the data. Third, why that makes it an unfair comparison with human performance? Well, when a fine-tuned model scores well, part of the score can come from those shortcuts. It memorized data-specific quirks rather than genuinely solving the task. A human never saw the training set. They just bring general ability to learn things. So comparing a fine-tuned model's benchmark number against humans is not fully apples to apples. The model's number may be inflated by shortcuts the humans never had. FuShot, by contrast, gives model a handful of examples in the prompt, much closer to how you would normally test a person, which is why the authors argue that it is a much more fairer comparison. Now that we understand what fine-tuning is, let's see what GPT-3 does instead. Now let's look at this one. 4 panels, same translation, English to French. We already saw this in abstract. This figure just arranges them on a spectrum of how much task-specific data each needs. They're essentially the new mechanics. Now, FuShot means k equal to 10 to 100 demonstrations packed into the prompt, delimited by lines, and of course, capped by the context size, which is 2048 token. Then there is the one shot. And then, of course, zero shot is the harshest. Sometimes unfairly, since make a table of world records is ambiguous even for humans. So here, the input is English and the output is French. Now, fine-tuning needs thousands of pairs and, of course, weight changes. FuShot needs 10 pairs in the prompt and no weight change. Now, the paper makes a sharp case about zero shot. Now, this is really important. Zero shot is the purest test. Only a natural language instruction, no examples at all. It gives maximum convenience and it is also the most robust against spurious correlations. But this is also the most challenging setting and sometimes unfairly hard. With no examples to anchor the format, even a human can struggle to what you want. If you ask a human to make a table of world records for the 200-meter dash, a person genuinely might not know the intended layout. So a low zero-shot score does not always mean the model failed to understand. Sometimes it means the task itself was underspecified. And the paper is even handed about FuShot, the same way it was about fine-tuning. Here's what it says. The main advantages of FuShot are a major reduction in the need for task-specific data and a reduced potential to learn an overly narrow distribution from a large but narrow fine-tuning dataset. The main disadvantage is that results from this method have so far been much worse than the state-of-the-art fine-tuning based models. And like we said, FuShot barely needs any label data. And because the weights never move, it cannot overfit to a narrow data set, the way fine-tuning can. Now, at the time of writing this paper, FuShot still trailed the best fine-tuned models. The entire rest of the paper is the argument that scale shrinks that gap. So the paper leads with the FuShot numbers, even when they sit slightly behind fine-tuned models. And one shot and zero shot stay the fairest comparison to human performance. The most important future targets. Now let's talk about how the model was tested. Now the paper talks about scoring each completion. It is tempting to picture that the model was just answering A, B, or C. But that is not what happened. This was not like a multiple choice question. For a multiple choice task, they never asked the model to emit a letter. Let me make that mechanic concrete because it is clever and not what most people picture. The candidate answers are given. It is a multiple choice, so the options already exist. The model is never guessing or freely generating. It is scoring answers it was handed. For each option, you build one string, the context followed by that option, and you push it through the model a single time. One forward pass to. As the model reads across the options tokens, it reports at every position how probable it thought the exact next token was. You never let it pick the next token. You feed it the answer you already have and just read the probabilities it would have assigned. Essentially, that trick, marching the model along a known target string and reading its token probabilities instead of sampling, is called teacher forcing. Now multiply those per token probabilities together and you get one number. How likely the model finds that whole option. Do it once per option, 4 options, 4 forward passes, and you take the highest. That's the entire multiple choice recipe. Hand the model the answers. The teacher force each one through a forward pass and let its own probabilities pick the winner. But there's slight kinks here. First, per token likelihood. A longer answer is made of more tokens, and every extra token multiplies in with another probability below 1. So longer completions almost always will come out with a lower total probability, just for being longer. To level that, they divide by the number of tokens and compare the per token average likelihood instead of total. Now, a 2-word answer and a 10-word answer are judged on equal footing. Second, on a small set of data sets, ARC, Open Book, QA, there is a subtler trap. Some completions are just common strings. The model rates them high no matter what the question was because they are likely English and not because they answered the question. So for those three, they normalize by the completion's own baseline. They take the probability of the completion given the real context and divide it by the probability of the same completion given a generic answer context. Literally the word answer followed by a colon or the letter A followed by a colon. That denominator is how likely it is just as an answer-shaped phrase with no real question behind. Dividing it out strips the background popularity and leaves only the lift the actual context gives it. Written as a formula, it is P of completion given context over P of completion given answer column. On the development set, this extra step helps on exactly those data sets. For binary classification, they give the option semantically meaningful names, true and false, and not 0 and 1, and treat it as multiple choice. Thank you for listening to part 1. Click on the link below for part 2. Do not forget to like, share, and subscribe, and let me know what other papers you would like me to read.